So we have Özge Sürer here to tell us about Bayesian analysis of nuclear dynamics. So Özge, take it away whenever you're ready.
Sure. Hi everyone. I'm Özge. I am an assistant professor at Miami University. I collaborate with Bayesian analysis of nuclear dynamics as a statistician. So today my talk will be about the collaboration, what we do, and mostly, I will not be talking about too much physics, so it will be mostly on the perspective. And feel free to interrupt me. I don't know how it will be, feel free to ask me questions if you have one during the presentation. So I will briefly mention about the theme, and then framework includes 4 different modules for computational tools, and I will be talking about them briefly. So our group is a multi-institutional and interdisciplinary group. So as the name suggests, we have a group of people who work on statistics and physics. And we started with 4 institutions, but then later it changed a little bit when people moved around. But our guy is Daniel Phillips, and he's in Ohio University. And over time we had then that is a postdoc, and I also started as a postdoc, and then joined as an assistant professor to the group. And then we have Alexandra, who is working on mixing models, and I'll just be mentioning about Bayesian mixing. In Ohio State, we have physicists and statisticians, and we have students coming from PhD candidates from physics and statistics, and then right now. And Michigan State, we also have physics and statistics in Michigan University as well. And lastly, I was at Northwestern University. I completed my PhD at Northwestern, and then I continued my postdoc there during COVID-19. And then in 2022, I moved to Miami University of Ohio as an assistant professor. So the main group of the band collaboration is to provide some statistical tools to the community, mainly for uncertainty quantification. And when we provide software tools, our goal is to have them nicely written, well commented and documented, so that the community can use it for their own problems. So this is why we have physics people providing their problems, and then statisticians who are also interested in computational work. So we try to combine these two. It is not that easy, of course. There are some challenges because we are not software engineers. We basically work on methodology, and it is a challenging thing to develop those software frameworks. And you can visit our website. So we deliver our products from our website. So the software tools, our publications, and then our software tools are kept under the GitHub framework. So here from the GitHub, it's an open source directory. You can access our software packages and also some instructions how to compile them, how to install them. And you can also have a framework and try it for your own problem. So right now, so we have the free version, and under that version, we have a couple of software packages to do uncertainty quantification. And as you can see, band framework has a version, but then the packages under that has different versions. So it is challenging because at a given time point, all of these packages should be able to work smoothly without any problem. So Surmise is a Python package that is something that I contributed during my starting from my postdoc. So we initially designed that package. So this is a Python code basically. We released it as a Python package. So anyone in the world can download the package, install it from, Python's own repository, so it is keep installable basically. And our goal was to include some statistical tools for emulation and calibration. And that could be an interface for different methods so that anyone can run those methods using our software package. Then we have mixing packages. So Samba is developed by Alexandra. And then later we have Tavaret. Tavaret is greater than Samba, meaning that Tavaret has 3 other mixing tools that can many PhD candidates work. And I will, I think, mention Tavaret and Thermite later. And we have a Python package for multi-objective simulation optimization. And ROSE is mainly developed for physics models for reduced order scattering emulation. And Emacs is also available as a web application so that you can actually try and see some quantified theoretical model predictions under Emacs. And our goal is not to deliver some Python packages. Our goal mainly, when we provide those packages, we want them to communicate with each other, basically. So there will be some physics models that are also code, and there will be some statistical models. Those are also code, and we want them to be communicating with each other. So we will have case studies. We have case studies, and we are working on them. So, for example, one of them is, I included the one that I worked on. So I worked with Philomena News. She wrote Fresco X during her postdoc. And what we did, we combined Fresco X with Surmise to illustrate how one can use a physics model with a statistical package. And we're always, we welcome contributions. At any time, you can communicate with me or other band members from our website. You can access our email. And we're open to collaboration and including, if you have your own statistical method or your physics problem, you can also contribute through our GitHub repository and contribute to the repo, and you'll be author of BAND framework as well. So as I mentioned, so we have 4 main computational tools under BAND framework. So we try to separate them, but they are actually connected with each other. But regarding methodological work, they are different from each other. So we have model emulation, model calibration, model mixing, and experimental design. So those are main working groups in our collaboration. Model emulation, so we have physics models. So here, S represents the physics model, and X and theta represents those physics models input. And we have a bunch of physics models. So K represents this different model. And model emulation is actually a predictive model. So you can call it a machine learning model, statistical learning model. So I'll call it predictive model right now. And it is basically cheaper proxies for those expensive physics models. Because, evaluating these models, it better than me, it takes time. And it is difficult to generate a bunch of predictions using this model. So we need these predictive models that can actually predict simulation output for a given input in a cheaper way. So we have people working on different model emulators. And then calibration, so those models have parameters that adjust the output. And we have some observations from physics experiments. Those are real experiments, not the simulation experiments. And we typically use Y to denote these observations. And model calibration is a way to infer these unknown model parameters using observed data from the experiment. And so, as I said here, different groups work on the same problem, and each group have different models, and there are high fidelity models, low fidelity models. And mixing, as the name suggests, is a way to mix or combine those different models to produce the best prediction of the simulation output. So we have a group of people who are working on these mixing problems. And finally, experimental design. This is something that I particularly work on. So there are two groups of experimental design people. Some people focus on simulation models experimental design that I will talk if the time lets. And there are people who work on real physical experiments. So here, basically, we have these calibrated models, and we have some observations at given points. And experimental design focuses on how to collect new experiments, where to collect these experiments. So the question that we look focuses on these fixed point experiments that we will be running with real experiments. All of these have their tools, statistical tools, and we combine them with physics models, and we include them as our study to illustrate it to the community. And I will briefly talk about emulators, calibrators, and four main modules. Basically, from my perspective as a statistician, we call them as simulators, the models, physics models that you have, or sometimes we call them as computer models. And we try to understand the real world using these computer models. And because of increasing complexity, their time complexity also increases. And we want to we try to come up with something to predict computer model output. So, but those are basically computer codes. And recently, there's an growing interest on uncertainty quantification because we want to understand whether we trust our predictions or not. And for example, here, Fresco, as I said, is a scattering code for couple channel calculation. So it is also publicly available at this GitHub account. So I am not the author of that package. And this is written in as a Fortran file. So when I started working with Davina Nunes on FrescoX, so basically I need to compile these Fortran code and then try to combine it with a Python code, right? But basically when I say simulator or computer code, I mean that we have some code and we define some input files. This is written, right, as a text file here that defines the reaction, the energy, some parameters regarding the reaction. And basically from your terminal, you install FrescoX and run this computer code to produce the output. So we need such models as an input in our statistical model. And we represent those computer models here with M. It has two types of input typically. The one of them is this unknown parameter that we try to understand this unknown parameter using uncertainty quantification technique. And we also have the controllable design input. And then it's a really mathematical function for us that takes those inputs and generates the output. And we typically, I think those YouTube people typically start, as an emulator, we typically start with Gaussian processes. Those are, I think, in machine learning literature, they are machine learning models, predictive models again. But the main difference from the rest of the traditional predictive models is that Gaussian processes provide, in addition to predictions, they provide some uncertainties associated to the prediction. So we can, it is very helpful to produce uncertainties about our prediction. But in order to be able to build these predictive models, we really need some sample of observations from our simulation model or computer model, physics model. And we generate some initial design for these input values. And then we obtain their output. We run this. So I run the Fresco app. It took about a day to only receive one output, for example. And then we use these outputs to produce these prediction models. And depending on the type of a model, for example, the way how you construct these model changes. For example, in my talk, the things that I will illustrate assume that this is a deterministic model, meaning if you run the computer code at the same input, the result is not going to change. But for example, I worked with Dan Leonage on his heavy ion reaction model. And then this was a stochastic model, meaning for a given input, the results were changing. So depending on the type of model, the models that we develop will be changing. And we use these emulators as, at the end of the day, those are prediction models, and then we produce prediction for those inputs related to. So here, this is a really basic illustration of a Gaussian process model. So I use Surmise and basic model. So here, I assume that I have a computer model represented by the red dashed line. And then what I did, I assumed that I have a computer model with a single point, just single parameter. And then I assume that those stars here, star markers, are my observations in my training data. And I use these three observations and train my Gaussian process model. As you can see here, with only 3 points, my prediction mean and the truth does not overlap. But if I increase it, for example, to 5, now they become closer. But as you can see, we also have some uncertainties on our prediction. So this is one good thing about Gaussian process. And if we increase it to 7, so we will have less uncertainty. So if we have a good emulator, meaning a highly accurate emulator, then we can incorporate these emulators into the calibration process. So when we talk about calibration, now we have additional observed data from the real physical experiment. And the goal here, now that we can predict output and at any input point, if we have some observed data, the goal is using this observed data in our emulator, can we find the best parameter that aligns the simulation output with the real data? So this is also in statistics literature, we call it an inverse problem, because right now, when we have this emulator from input to output, the calibration is an inverse problem because we try to estimate the parameter values using observed data. And typically, I don't want to go into detail. So in Bayesian calibration, we typically use Bayes rule that we represent the posterior density of the parameters using the likelihood and the prior. And the problem here, prior is typically given by the domain scientist to us. So it's basically what is the possible region that this parameter can lie. And it is difficult. It is easy to compute because it's a closed form, typically function that for a given parameter we can compute the prior. The problem here is the likelihood, because it is not a closed, it doesn't have a typically posterior for complex model, does not have a closed form solution. And we typically use sampling methods such as Markov chain Monte Carlo method, get some growth from the posterior. And likelihood in these sampling methods, we typically need thousands of evaluations of a simulation model. And if the simulation model is complex and time consuming, we need emulators within the sampler. And likelihood here requires the simulation output. So this is where we use our emulators to compute our likelihood for a given parameter value. And basically, if I use the same simulation model, toy problem that I illustrated, suppose that you have, I just here overlay 3 possible outputs of a computer model. And suppose that these blue dots represent our observed data from a physical experiment. Then our goal is to find which parameter is the best parameter that describes the real data. So here, as you can see, the orange one looks like the best one, right? That describes these 5 dots here. And I use a sampler here to get the uncertainties on my parameter. So if we have this posterior distribution of the parameter, so again, this is a toy illustration, then we can propagate these uncertainties on the parameters onto our predictions, simulation output predictions, because our goal is to understand the reality. So we can actually come up with some uncertainties on the simulation output side. And Surmise, as I said at the beginning, so we developed this package as a Python package that can do some emulation and calibration strategy. So it includes different methods under these modules. And it has basic input-output definition. So we provide some training data and we select the method and we just build the emulator. So what we did, we included some Gaussian process emulators under Surmise. And we also included some methods that we worked on. So for example, here, this is a GP model for high dimensional output. If simulation outputs have some missing values. So we have some physics example that has missing output. So we have an illustration how one can use emulator for their physics example. And we have some publications that show how, so this is the first one is the model itself for the missing observed output for the simulation model. So this is basically a statistical one. And then we have 3 different implementations of the Surmise package for different physics models. So for example, this one that I mentioned, the simulation model was not a deterministic one. So we needed to come up with some stochastic model for this example. So mixing, so we have I think, great interest in our group regarding the mixing model. The mixing, as the name suggests, so we have a bunch of models after we do calibration. So for example, think about you have this blue model calibrated, and then the red one, so you observe the data, for example, 1, 2, 3, 4, 5, so these 7 points. And then we have basically the goal here, how we should combine these 2 models so that we can predict the real data correct. So the goal here is to find a weighted average of these different model predictions, basically. But of course, these weights are the research itself. So it is important to come up with different models for mixing procedures. And so we have 3 great people who worked on these mixing models under band. And so we have those contributions are combined under Tavaret. So Tavaret is released under band framework, and then it has a nice documentation. So this was one of the great work under band, because these people that you see, those are early career scientists, and it includes people from different institutions and different disciplines. So we have physicists and we have a statistician here. So they just released their Python package, also the publication. And the source code includes 3 different mixing approaches. And they all have separate publications, which illustrate how one can use these different methods for a physics application. And basically, in their code, we need to define different physics models. So calibrators, as you can see, those models do not include parameter because we assume that the parameters are already estimated. So those are calibrated models. But of course, a different approach can be how to combine the models that are not calibrated yet. And then if you want to use one of these models, you can use the existing mixers, or you can create yours and include under this base mixer class. So this is a Python package, and then train your model to obtain weights and the mean prediction. So if you're interested in how the code is written, so that you can find the Python package and the paper associated paper. But this is the main class. So I think I don't know how I am doing this time because it's quite late. But just I want to briefly mention about experimental design, and if you are interested in talking about this, I'm happy to discuss because, as I said, so I am working on the experimental design side. So we have two main questions in experimental design. The one of them is how we should design these computer experiments, right? In order to build emulators, we start with some training data. So one research question is how can we construct these data sets to have some accurate predictive models? And the second one focuses on designing physical experiments. And I am interested in both of them. So I will be showing this one for this talk, and hopefully when I have a paper published, I will be talking about physical experiments. But what I did in this research, my goal, so I worked with a couple of physicists during my postdoc, and the thing was we focus on uncertainty quantification. So we build emulators, and then we use those emulators for calibration purposes. And I realized that even though we make sure that our emulators are good enough in terms of predictive accuracy, we realize that if the purpose is calibration, we should do targeted sampling. So my first paper was focusing on this, how to do sampling in order to better learn the calibration region of interest. So what I developed is, so here, if we do not, so in my research, I focus on sequential data collection because sequential approaches are useful because we can actually, using the given information, we can collect more data. So it allows us to do targeted data collection. So here, this example is just, so these lost markers is just space filling design if we have two-dimensional parameter space. And these contour plots are the posterior region for this parameter space. So basically, if you do space filling design, so it is a traditional design where anyone, if someone is interested in statistical perspective of these physics models, I think this is the first thing that we do. So we gather some data using space filling design. But again here, if we are interested in this contour line, right, this is the high posterior region. Do we need to sample here? So the question that we looked for was that. And then we come up with an acquisition strategy. So where we created a metric that allows us to do targeted sampling around the region where we focus for calibration purposes. So in sequential sampling, we typically come up with some metrics to allow us, to do focused sampling. So I'm not going to talk about our sampling criterion, but you can find more in our paper, and the next one is coming up as well. And again, I'm happy to talk if someone is interested in statistical perspective for building, good emulators. Good emulators mean, predict highly accurate emulators for calibration. So I won't be, going into the details, but I think at this point, I can take some questions about Ben and how, what we do in terms of uncertainty quantification.
Okay, thank you. Okay, questions? Yeah. All right. Yeah.
Do I just shout or the mic or something?
Let's ask, can you hear the speaker or the question asker?
You can hear me, right? Okay,
Go ahead.
I got actually 3 questions because what you are doing is quite impressive. I do think emulator is a way to speed things up. So about the last part where you talk about sequential calibration, don't you think you will run into risk of being stuck in a local minimum or maximum because you are sampling in the proximity of your maximum or minimum? That's the first question.
I think that's a great question. So for this reason, because of this, we can always get stuck in some local optimal regions. For this reason, our acquisition strategy focuses on the uncertainties of the posterior density. And if we focus on the uncertainties, that strategy allows us to focus on highly uncertain regions. So basically, if there are multi-dimensional posterior regions, then it will be actually locating the point on these multiple high posterior regions, because our acquisition strategy is to focus on the uncertainty. So it allows us to explore these high certain regions with the acquisition strategy that we selected.
I get it. Okay, yeah, thanks. That makes sense because in the unsampled region, the uncertainty is larger. So you can ask the emulator to go to those phase space when you have enough points on one particular region. I got it. Thanks. My second question is on slide 22. So I think what you are trying to do here is to marginalize over the hyperparameters, right? But I've seen people, in fact, I did in an alternative way to select those parameters, which is simply to maximize your leave one out cross-validation results and just fix your value of theta. Do you know if there's any advantage or disadvantage to doing that? Are you familiar with the cross one out, leave one out cross-validation method?
Yes, I think the way how we define is to come up with a single estimate of the parameter, right? Sometimes we can, for example, if we think about the posterior as an objective of our optimization model, we can find the parameter that maximizes the posterior, right? But it will not produce us any uncertainties, right? It will be a single point estimate that will give us the highly accurate predictor, right? But it will not help us to come up with uncertainties. So since, mainly we focuses on Bayesian uncertainty quantification as a methodology, right? We do not do point estimates, but we also come up with some uncertainties about the parameters.
Okay, got it. My final question is because I used to work on nuclear equation of state where I don't want phase transition, so I want it to be monotonic. So my question is, are there ways I can force Gaussian process to be monotonic?
So you are saying that your outputs are monotonic. It doesn't have any changes. So
go on, sorry.
So your question is...
No, not that there's no changes. I want it to keep increasing because let's say you have an equation of state. If you have a valley, that means you have a phase change, right? Sometimes I don't want a phase change. I want the pressure as a function of a baryon density to just go up and up in one direction. Are there ways I can force the emulator to just move in one direction?
So if I understand the question, so you're saying you have multiple outputs, right, from the physics model that you described. And then so Gaussian process will be a predictive model, right? If you sample enough, I think it will be able to predict the shape of the output that you come up with. And Gaussian process has some parameters such as the kernel function, the covariance function. And depending on the shape of your simulation output, right? If it is, monotonically increasing, if it is smooth function, or if you have some maybe, very abrupt changes in the output. So you can choose the kernel function appropriately to understand the shape of the output. So was that, I don't know if I answered your question.
And so not really. So what I used to do is to generate equation of state with Gaussian process. But Gaussian process, it's random, right? It just go up and down. I want a Gaussian process to be monotonic, but maybe that's too technical. I think maybe I should ask you after this meeting.
Yeah.
Thank you for answering.
Not a problem. Thank you for the question.
Thank you for
Yeah, I think there was another hand up as well at some point. Two. Okay, so maybe here first.
Thank you for interesting talk. I have a nice question. So you said that you can mix different models. I'm wondering what's the physical interpretation of mixing different models? Does that create a new model?
Yeah, exactly, right? That new model, so suppose that you have this blue one and it only predicts this region, right? From -3 to +3. But you have another model is able to predict from 0 to 6. If you combine them, so you will come up with some weights. And probably in the simple question, the weights will be, if the region is around -3 to +3, use blue one for predictions. And then in this region, right, combine them equal weight. And then for that region, use the red one. So basically, it will assign weight for each model. And then for a given input, you will have an access to your mean prediction at any location, right? Because of the weight, because it will learn the weight from your data set.
Well, in this case, that these two models cover different phase space. What if you have some models that can cover the same phase space?
Like here, same model covering the same space, two models?
Yes. For example, if we have two models that can cover, both can cover from -2 to 6 years, is there any meaning to combine them?
So yeah, you can combine them, but basically that combination will tell you right here, don't use red one, or like, I don't know if red one is some weird predictions that are not aligned with your true data, right? It will assign 0 weight to that model, but weight 1 to the other model, right? It's like a weighted average of these model predictions. So here, for example, we have two models overlapping, and both of them are doing a good job. So your mixing model will probably say that use 50% of this model prediction plus 50% of the other model, right? Mixing in the equal weights. So basically, when you mix it, you will be accessing the mean prediction, the model's weight, so you will understand that, okay, the first model is really good at this region, but the second model is doing a good job in the other region. And you will also, when you combine them, you will also come up with some uncertainties, right? Maybe you have an accurate model, right? Many accurate model in one region, so your uncertainties will lower in this region. But maybe you will have many models that are not doing good job in some regions, so your uncertainties will be higher in this region.
Well, so that both things in the aspect of computation. Then what about physically, how to interpret this new model?
So physically, you can write like so those are our physics models. So when you see the, I think, weights, you will understand that which model is doing a good job in predicting certain input spaces, right? I think, and because of interpretation, there are also some other methods, right? If a domain site is interested in the interpretations, typically we say sparse models are better, meaning, instead of having too many models with smaller weights, sometimes we prefer model selection instead of mixing, right? So in which region, at a given region, which model is doing the best job? So you can also have this kind of selection interpretation.
Okay, thank you.
Yeah, go ahead.
Hello, my name is David. I was actually wondering, so I'm not too familiar with Bayesian analysis, but from what I could tell from your presentation, if I had some physical process where I knew some sort of functional form, would I be able to use this kind of band framework to try to figure out the parameter space for that function that would fit my data?
Yeah, exactly. So you need your model, right? That function, and then if you want to calibrate, we need some also observations from the real experiment. And then basically, for example, if typically, right, when we start working on different projects, I realized that each problem requires some kind of fixes because of the nature of the model. But right now we have some emulators. So basically what you need to provide some inputs and their outputs using your function evaluation, and you will be choosing the appropriate emulator and then the calibration technique, and it will produce some uncertainties for your parameters and the predictions.
And so where you see method, how is that? What's in between the method and the function? Is the method just how it's internally simulating the output from that function model, or?
So method here is, so X, theta, those are the inputs that you evaluate the simulation model, and then you collect some data. So this will be kept under F function, basically. I mean, it's an array, right, in the code, basically. The method is, so this one, for example, is a Gaussian process, but PC stands for principal component. So it is written for the output when we have multi-dimensional output, because many methods that I work with physicists, their outputs are multi-dimensional, meaning for a given input, it produces multiple outputs. So this PCGP is for high-dimensional output, basically. But we have, usual GP under Surmine. So this one, for example, Moses's PhD work, that if you have some missing outputs in your observed data, the simulation output, so we have different approaches under Surmine that you can directly, use your own evaluations and check your emulation quality and calibration results.
Okay, thank you.
You're welcome.
Okay, any questions from the Zoom? Any more from the room? Okay, thank you again, Özge. Let's do it.